Hello again. In this video, we're going to begin talking about the material from section 3.3, which is about the rules for derivatives. Now, in the previous section, we introduced the limit definition of a derivative, and we found the derivative of various functions using that limit definition. But oftentimes, it can be very tedious to find the derivative of a function using the limit definition of a derivative. So our goal in this section is to come up with some rules and formulas that we can use to quickly evaluate derivatives without having to go through the limit definition of the derivative. Now, one thing I want to remind you of is every rule that we talk about comes from the limit definition of the derivative. These rules do not come out of thin air. They're all based upon the limit definition of the derivative. Okay, but once we establish these rules using the limit definition of the derivative, then we're just going to find the derivative using these rules instead of going through the limit definition. Okay, so the first rule tells us what the derivative of a constant is. So if c is a real number, then the derivative of c is equal to 0. Now, if you think about this, this makes perfect sense. Suppose you have this constant function, f of x is equal to c. If you were to graph a constant function, of course, it's a horizontal line. And if you were to find the derivative of this function at any point x, you would find that the derivative is 0. And the reason is because the derivative is the slope of the tangent line at this point x. But the slope of the tangent line is also this horizontal line, and the slope of a horizontal line is 0. Another way to think about this is the derivative also gives you the instantaneous rate of change in the function at this point x. And this constant function is not changing. That's why it's called a constant function. And so the instantaneous rate of change at any point on this constant function would be 0. Okay, so that's our first rule. All right, the second rule is called the power rule. And it says the derivative of x raised to the n power is n times x raised to the n minus 1 power. Now, this theorem says that n must be a positive integer, but this can actually be extended so that n is any real number. So this is actually true not just for n being a positive integer, but it's also true if n is any real number. And later on in the book, they do mention this as another theorem. But I think it's important for you to go ahead and realize that this rule is true for not just n being a positive integer, but for n being any real number. Okay, so that's called the power rule. So I want to practice both of those rules by looking at these three derivatives from example 1. Okay, so the first one, we want to find the derivative of x raised to the n power, or x raised to the 9th power. And we're going to use our power rule to do that, which says that the derivative of x to the n is n times x raised to the n minus 1. Okay, so in this case, the derivative of this using the power rule should just be 9 times x raised to the 9 minus 1 power, which of course is 9 times x to the 8th power. So if you go through the limit definition of the derivative, you would find that the derivative of this function would simply be 9x raised to the 8th power. Okay, what about this one? The derivative of x with respect to x. Well, notice that this is x to the first power. We normally don't write the first power here. Normally we just write x, but it really is x raised to the first power. So you can use the power rule here, and you would just get 1 times x raised to the 1 minus 1 power, which is just x to the 0 power. And x to the 0 power is equal to 1. In fact, any number raised to the 0 power is equal to 1. And I think this is important to remember because you're going to be taking the derivative of x quite a lot. Okay, And so the derivative of x with respect to x actually is equal to 1. Another way to think about this is if you were to graph this function, y is equal to x, it's simply a line that has a slope of 1. And we know it has a slope of 1 because in y equals mx plus b form, m is the number in front of the x. Okay, so m is equal to 1 here. And if you were to find the tangent line at any point on this line, y equals x, the tangent line would be the same line. And so the tangent line at any point on this function would have a slope of 1. So that makes sense. Another way to look at this, just so you know, is when you take, this is called the derivative operator, and it operates on whatever's in the parentheses next to it. So this means take the derivative of x with respect to x. But this is equal to dx over dx. That's another way to write it. They're equal. And you can sort of think of this as being the same, and so it's equal to 1. Right? Whatever dx is on top, you have the same dx on the bottom. Those are equal. And so this would just equal 1. Okay, and we'll see later on that this actually can be thought of as a division sign. And we'll actually define what dx is in the future. So we're not going to go into it now until we get to some section in the future. But whatever dx is, we'll define that quantity later on. It's the same on top and bottom here. And if you think of this as a division sign, then they cancel out and you are left with 1. So there are several ways to think about this. Okay, part C, we're finding the derivative of 2 to the 8th power with respect to x. But 2 to the 8th power is simply a number. It's a constant. So the derivative of it should be 0. Okay, so let's look at some more rules. Okay, this rule says that the derivative of c times f of x, a function f of x, is simply c times the derivative of f of x. Now, c is a constant here. Okay, so what it's really telling us is that if you're taking the derivative of a constant times a function, you can actually take the derivative of the function, f prime, and then multiply it by the constant. So it's sort of like this constant can come outside the derivative operator. Okay, and so let's just do a couple of examples where we use this rule. So this one, let's say you want to find the derivative of this. The constant here is really negative 7 over 8, and it's being multiplied by x raised to the 11th power. And so we're allowed to sort of pull this constant outside the derivative operator. Okay, so these are equal, and now I can just find the derivative of x raised to the 11th power using the power rule. And of course you just get 11x raised to the 10th power because you subtract 1 from this exponent, and then I can multiply it by this constant, negative 7 over 8. Okay, and so just to finish this off, you get negative 77 over 8 times x to the 10th power. Okay, so that's the derivative there. Now let's look at this one. Now in this one, the constant is 3/8, so that can be pulled out in front of the derivative operator. And then anytime you have radicals like this, you always can write radicals in terms of some exponent. And so the square root of t is the same as t raised to the 1/2 power. And you're going to want to do that because if you write it like this, then you can use this power rule. So you should always write radicals in terms of exponents so that you can use the power rule. Now, you may or may not remember this, but just as a reminder, this bottom number is the index of this radical. So that's why this is square root. And then the top number is what you're raising the radical to. So you can think of this as square root of t raised to the first power. And if you write this as an exponent, then it would be t raised to the 1 over 2 power. Okay, like as another example, let's say you had the cube root of x squared. If you wrote that as an exponent, it would be 2 divided by 3, the power divided by the index of the radical. So it's x to the 2/3 power. And you should always, again, write radicals in terms of their exponents before you take the derivative of them, so you can use the power rule. Okay, so let's go ahead and find the derivative of this. Using the power rule, the 1/2 would come down and get multiplied in front, and then you subtract 1 from 1/2. Of course, you want a common denominator here, so instead of writing it as 1, let's write it as 2 over 2. And that way you can add these fractions or subtract them, and you get negative 1/2. And then you multiply this by the constant 3/8. And so it looks like you get 3 over 16 times t to the negative 1/2 power. Now remember, negative exponents can be written as positive exponents as long as you move them to the other side of the division sign. So if this is in the numerator, then you can write it in the denominator with a positive exponent. So it's actually t to the 1/2 power in the denominator. Okay, and then this is just square root of t. So you could also write it like this. And that's your derivative. Okay. Now, one thing I want to mention here is notice that you're taking this derivative with respect to t, but the independent variable here is t. Okay, and so this makes sense. Later on, we'll learn about what happens when you take the derivative of some function with respect to t, but the function depends on x. Now, we're not going to talk about that until a later section. For now, every time you take a derivative, these letters should match up. Okay, so we're taking the derivative with respect to t, and the only thing we know how to work with is functions that would depend on t here. Just like up here, this function depends on x, so we only know how to find the derivative of it with respect to x. Okay, the next rule is called the sum rule. And it basically says that if you want to find the derivative of f plus g, two functions added together, then it's simply the derivative of f plus the derivative of g. And you really can think of this as being a plus or minus. So if these were subtracted, the derivative of f minus g is the same as the derivative of f minus the derivative of g. So you can think of this as both a sum and difference rule. Okay, so let's look at this one. Now notice I'm taking the derivative of this with respect to w, but this function does depend on w. Okay, and so according to the sum and difference rule that we just looked at, I can actually break this up and find the derivative of each of these individually, and then add or subtract those derivatives. Okay, so let's do that. So this is the same as the derivative of this, plus the derivative of this, minus the derivative of 6w, plus the derivative of 4. Okay, and then I can pull the constants outside these derivative operators. And then the derivative of a constant is equal to 0. Okay, now we're just left with a situation where we need to apply the power rule. So to find this derivative, you would just multiply by 3 and then subtract 1 from the exponent. So it's going to be 3w to the second power, and then you're going to multiply that by the constant in front. Okay, this one's going to be 2w raised to the first power, and then multiplied by the constant. This one, the derivative of w with respect to w is simply 1. Now, if you don't remember that, you can use the power rule. This is w to the first power, and so the 1 would get multiplied by the w, but then w would be raised to the 0 power. And w to the 0 power is equal to 1. And then that gets multiplied by the 6. Okay, so just to finish this off, this is 6w squared plus 18w minus 6. Okay, so those are kind of the basic rules of derivatives. You should get familiar with those rules. And then later on in this section, we'll talk about how you find the derivative of exponential functions or the natural exponential function. And then we'll talk about higher order derivatives as well. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.